Good afternoon, everybody. Today we will be continuing our discussion on applying Newton's second law to solve problems. In particular, we will talk about how to calculate static and kinetic friction. Before I start, I want to make an announcement regarding our midterm 1 that is coming up in 2 weeks. So let me share my screen with you so I can show you some information. This is under the exam folder, but I will make sure I post this information in the announcement, so you'll be able to get an email notification. It will be on March 9th, which is 2 weeks from today. And the exam will be online, available for 24 hours on March 19th. So it will be starting from midnight of that day until the end of the day, 11:59 p.m. So during the 24 hours, you can choose any 2-hour period to do this at your best convenience. Try not to pick 2 hours that you're not distracted by anything else. You can access on Blackboard. The content we will cover will be the beginning of the class, where we talk about dimensions and units on the first day, to the kinematics, and then the dynamics, that's the Newton's laws. So it will be from the beginning of the class until our end of our lecture on March 2nd. That's when we talk about the last class of Newton's laws, okay? So that will be covered on midterm 1. There will be 20 questions. Some of that are conceptual. There are some calculations that you have to enter your numerical answer. And I posted a practice exam here with the solution. So you can try to do this on your own for practicing purposes. And what's allowed, it's open book and no open notes, but no collaboration. So the Discord side, try to disenable that on the exam day, and do not talk to others while you're doing your exam, okay? Are there any questions about the exam?
For the exam, is it, yeah, it says it's all multiple choice on there. But anyways, will the practice exam cover all of the test, or should we study other stuff as well?
You should always study beyond the practice exam. So the practice exams really just sort of show you what the level of the question looks like, you know. But like I said, when we say for every 1 hour spent in the class, spend 3 hours outside of class, that's all for try to study it, that including doing homework and looking at the other materials, take a look at your textbook and do some extra problems at the end of the chapter. So those are all what will make you be able to solve the problem eventually on your own, right? So when you are preparing for the exam, a good way to check your understanding is, okay, let's say I'm practicing my understanding of 2D motion. So I'm going to take a problem, wherever you find the problem, whether from your homework or our example problem in class, I'm going to try to work it out on my own to see if I can do it. If I can do it, I'll move on to another problem. If I couldn't, I try to see the solution and then try to do it again. So just check your understanding that way. So you will know that you will be able to solve the problems on the exam. The practice exam is definitely good practice, but I would say don't limit yourself to just that, okay?
All right, thank you.
And is it only multiple choice? I'm getting some answers over questions over here. It's multiple choice, yes, in the sense you have to select A, B, C, and D. There are some enter your answer kind of type of question where it's there's let's say the answer would be 2 newtons and you have to enter the number. So those kind of questions require that you actually do calculations. So it's not just conceptual, but it's in the way that it can be done online. So that's the best we can do with this format. It will be on Blackboard, yes. And you simply open it up and the exam will show up in Blackboard. You either enter your answer, like select A, B, C, or D, or E, or you enter numerical answers. You don't have to take pictures and nothing is needed in that regard. There is no extra credit questions on the exam. And exam is going to be March 9th, and I will send out announcements again, okay? Chapter 1 to 6, in the sense that that's the corresponding chapters in the OpenStack textbook for kinematics and dynamics. I'm sorry, you have a question?
Yeah. Do we have to do the practice exam? Like, is it gonna?
No, it's not. That's just for your reference. You can look at it, or you can look at some other resources. That's totally up to you.
Okay. And how long do we have to finish the exam?
The exam is 2 hours. There's a time limit.
Okay. And do we have like the whole day to finish it, or are we gonna be staying on the Zoom with you until we finish it and then we can leave?
We won't be meeting that day. We will not have class. You can use our class time to be part of your exam time, or you can choose another 2 hours to do the exam. But the exam is timed. As soon as you open it up, it starts counting, right? It's 2 hours. But you can choose any 2 hours in that day, morning or in the evening, whichever 2 hours you want to do the exam is up to you.
Okay, thank you.
Equation sheet wise, because it's open book and open notes, however you want to organize your stuff is up to you, whether you want to write it up, summarize everything on a piece of paper so you can quickly reference it, or if you have your book in front of you or notes in front of you and you open things up, or on your computer, that's totally your choice, okay? The extra credit will just be the pre and post assessment. Okay. All right, now if you think of any other questions about the exam, just don't hesitate to shoot me an email or just let me know, okay? All right, we'll continue our discussion about Newton's second law. First of all, let's do a quick check-ins to see if we still remember how to draw a free body diagram correctly. So now I have a block that's sitting on a ramp, not going anywhere, staying at rest. Can you draw the correct free body diagram, labeling put all the forces on the block? So I'm gonna let you vote, okay? Okay, just a few seconds. If you have any last minute vote, please put it in. Okay, any last minute vote before I close it? Okay, let's take a look at this together. I'm gonna go ahead and end the poll. And here is the results. You can see we're quite split between choice A, B, and D. Okay, now let's take a look. So what do we say about drawing free body diagrams? What are the steps? First of all, you isolate the object that you're interested in, right? In this case, we're interested in a block. Second, you think about, okay, what other objects that the block is in contact with, because these other objects will be exerting a force on the block. So the only force that does not require contact, do you still remember what force that is? That's a long range force. What force is that? Does not require, that's the gravity, yes, gravitational force. That is the force exerted on the block by Earth. So I'm gonna label this force as gravity. So that's in what direction is gravity pointing at?
It's always down.
Always downward, very good. So this is our gravity, F of G, you can label it like that. And the block is also in contact with the ramp, with the slide. So in this case, the slide will exert a force on block, right? So what force or forces that the slide will be exerting on the block?
It exerts a normal force, which is perpendicular to the surface of the slide.
Perpendicular to the surface of the slide, very good. I'm gonna pointing upward, normal force. So that's choice A, these two, right? Are there any other forces?
Force of friction, because it's staying still.
Staying still, if you don't have a friction, it's gonna slide down because that's the component of the gravity that's along the direction of the ramp. It's gonna make it slide down this way, but it's not sliding down. So you must have a friction pointing in which direction? Not this way, but up the ramp, right? Along the ramp, but upward. So that's your static friction. It's static because the block is not moving relative to the slide, right? There, see, it's at rest. So it's static, there's no motion. So these three forces are forces that you're going to draw. So D is the correct answer, okay? Three forces. These two are actually components of gravity. Y components of the gravity. You decompose, when we start calculating it, we break down the force of gravity into two components. One is along the ramp, one is perpendicular pointing into the ramp. But on your free body diagram, you cannot draw them as separate forces because we only have, that's still just part of gravity. So now let's review how we calculate these forces. This is on the handout that I included in the weekly folder. It's simply just a box that's sitting at rest on the ramp. To draw a free body diagram of the object, well, we kind of already did, right? The gravity or weight, normal force, and static friction, three forces. In this case, you break the gravity down into X and Y component. So once you have done that, I recommend kind of cross out gravity or weight to show that you have already considered this force. Now it's being substituted by Wx and Wy, okay? Now we break it down in these two directions because it is easier to calculate. We put our X and Y coordinates instead of sort of what we normally would do it this way, right? We rotate it so that X is parallel to the surface. This is allowed for simpler calculation. So the question is, let's find the normal force and let's find the friction. Right, so this is what we have already done. So if you refer to what we did with the frog question in the previous class, we apply Newton's second law, that's the physics that's involved, to the object, and F net equals MA. You apply it in two different directions, right? You apply it first of all in the Y direction. In Y direction, F net in the Y direction is equal to FA in the Y direction. There are two forces in the Y direction. One is a normal force pointing up. One is the part of the component of the gravity in the Y direction. That's two of them. One minus another equals 0 because there's no acceleration in Y. So you found the normal force is Wy. which is weight times. Okay, still remember the WY is W times cosine theta or sine theta. Still remember that? The rope, the ramp has angle theta. Also, looking at the geometry, we know that the angle between W and WY is theta. This is 90 degrees. So the Y component WY is W times cosine theta or sine theta. It's cosine. Thank you, Eric. It is cosine theta because the cosine is the adjacent line of the triangle, which is the WY, right? So you can calculate this way. So if you want to replace W using mg, if you know the m, that's fine. Or if you're giving weight directly, you can just use weight. So that's the normal force. And you do the same thing in the x direction. You have friction pointing up. You have x component gravity pointing down, and it's at rest. So MA in the x direction, acceleration is also 0. So the friction has to cancel out Wx. So Wx is going to be mg sine theta, is the other side of your triangle, right? The opposite side, so that's sine theta. So one of them is mg cosine theta, one of them is mg sine theta for the static friction. Okay, so that's just a quick review of what we have went through. Now, if you're curious about drawing this angle, again, here's another diagram to show how these components break down in terms of mg cosine theta and mg sine theta. The trick is to remember if the ramp is 30 degrees, then this angle is the same angle, 30 degrees. Okay. Now let's look at static and kinetic friction in a little more detail. Static friction, though, can change because it implies it's relatively at rest. So let's say you pull the table and you can pull on the table a little bit force, you can say 5 pounds is how strong you pull the table. The table is not moving, which means the static friction is balancing the force. But if you pull really hard, 50 pounds is the force you acted on the table. It's still not moving. So the static friction must be 50 pounds to cancel out the force that you're exerting. So static force friction really changes based on the other force that is balancing, right? It's always going to equal to the force acting in the opposite direction. Kinetic friction, however, is a fixed value. Kinetic friction is always proportional to the normal force acting on the object. So it depends on 2 factors. One is how smooth or how rough your surface is. That's reflected by the coefficient of kinetic friction, which is just a constant. Another is it's related to the normal force. So if you look at, for example, if I have a block right here, right? And if your mu is 0.5 versus if mu is 0.2, this is more smooth. This is more rough, right? Where you have a bigger mu, it's gonna have a bigger friction. If it's moving this way, you're gonna have static friction in the opposite direction. Also, it is proportional to the normal force. In this case, the normal force is gonna balance out gravity. But let's say if you push on it, right? You push really hard into the surface. Does that make it harder to move? It's really hard to move now because you push it in, you're increasing normal force. Normal force increased and your friction also increased. Okay, so friction depends on these 2 forces. And I'm actually gonna get rid of the little vector sign because friction and normal force obviously are not in the same direction, but the magnitude of friction is proportional to the magnitude of your normal force, as well as what kind of material you're talking about. Is it made of, if the surface is made of sandpaper, it's gonna be really rough. Or if the surface is made of silk, or is it ice, it's gonna be really smooth. So remember the problem we did previously? we kind of, we slide a book across constant velocity across the table, but I left it, the last question of what is the force I applied, which is equal to the static friction. We didn't really say what the static friction is, but now we can solve the problem. The forces in the horizontal direction is the force of your hand balancing out the kinetic friction because it's a constant velocity. You have zero acceleration. And the static friction in this case is mu times the normal force. So the normal force is equal to your weight. So the static friction is mu times n, which is 0.2. That's the coefficient of your surface times the weight of the book. That's half a pound, which means the force of your hand is also half a pound. It's equal to the static friction. You keep it moving at a constant velocity. Okay, so because we know this extra condition, we're able to finish this problem now. To summarize, what we talked about, static friction. Remember, static friction varies. It always changes. It depends on how strong the force is in the opposite direction. Now, if you were to look at a frog on the ramp, depending on the frog situation, whether the frog is at rest, which means you have static friction, or if the frog is sliding up or down, doesn't matter, as long as it's moving, then you have kinetic friction. And those two needs to be calculated differently. If the frog is at rest, now if the frog is at rest, let's draw the free body diagram of the frog, which is you have gravity, you have normal force, and it's at rest, right? You must have static friction to balance out the component of gravity. The component of the gravity, again, I'm going to use a different color to show that this is just a component of gravity is Fg in the x direction, is mg sine theta. We talked about this already, right? So static friction is mg sine theta. But if your frog is moving, let's draw the free body diagram again. You have gravity, you have normal force. Let's say it's moving down, which means your kinetic friction is pointing up, F kinetic, is mu times N. Okay, so your normal force, what is your normal force? Normal force is Fgy. The y component of gravity, which is mg cosine theta. Therefore, your friction is going to be mg cosine theta. Let me get rid of this vector signs. Okay, so these two are different values. Okay, you need to figure out the friction situation depending on whether it's at rest or is it moving. There's one other fact about the static friction which make it very confusing and people often get this wrong. We said static friction varies. It can increase as your force increases. You can pull the table a little bit or you can pull the table a lot, but there is a limit of how much static friction the surface can provide, right? Because if you pull really, really hard, eventually you're gonna be able to pull the table and make it move. So which means between your table and your ground, there is a maximum static friction that the surface can provide. That maximum amount turned out to have the very similar expression as your kinetic friction. So that's why people got confused. So the maximum amount of the static friction that surface can provide is a coefficient times normal force. Again, it's proportional to the normal force, it's proportional to the surface, which makes sense. If you have a very rough surface, you think the surface can provide a bigger static friction. If you have a big normal force, right? Like say you put a lot of heavy object on your table, will make it really hard to pull because there's gonna be a big static friction that the surface can provide. This formula is exactly the same as this one. The only difference is when you're looking at the maximum value for your static friction, you use a different coefficient than your kinetic. It's slightly different for a surface, okay? But once you break this value, once you pull it really hard and it go over the maximum value, the object started moving. And once it started moving, you're gonna have a kinetic friction, not the static friction, okay? So we will be able to solve a problem today in class that has to do with the maximum value of static friction. So hopefully these ideas can become a little more concrete later on. So let's, this question help us sort of thinking about all the influences of the forces at play, right? When you're evaluating the motion of the object, you have so many forces and they're all coming together to play a factor in how the box moves. So this question help us understand what is changing, what forces are increasing and what is decreasing. So let's say you have a box 6 on the flat board, have a box here, you lift one end, right? First you lift it up just a little bit and then you lift it up a lot. So eventually your box starts to slide down, right? So how do we explain it in terms of the different influences of the forces? So I'm gonna let you discuss this question in your breakout rooms and then make sure you take a screenshot before you go. Maybe a couple minutes, okay? Please put in your vote for the question as people come back. Another 15 seconds. Okay, any last minute vote? Let's take a look at this together, okay? I'm going to go ahead and close it. This is our voting results. All right, so there are multiple factors in play when we talk about the motion of the object. So can anybody tell me when the flatboard is lifted up and the box right now is still at rest, okay, it's not moving yet. How many forces is acting on the block? Or you could just start naming the forces one by one.
Gravity.
Gravity, okay, and?
Normal force and friction.
Normal force and friction, very good. All right. You also know that the maximum amount of friction it can provide. So you can see this as you lift this up, in order to prevent it from slipping, the friction that you need is getting more and more, increasing more and more, because it needs to balance out the component gravity. So along this direction of X, along this direction of motion, the force that's responsible for trying to make the block sliding down is F of G in the X component. I'm gonna cross out G, right? The force that's responsible for preventing it from sliding down is the static friction. So both of them are playing here. So what is F of G? F of Gx is the X component of gravity, which is the weight of gravity, which is mg, this is mg, times, again, I'm gonna ask this over and over again, cosine theta or sine theta?
Sine.
Sine theta, very good. Okay, and as theta increase, sine theta increase or decrease? So let's say theta increase from 30 degrees to 60 degrees. Is sine theta increasing as well?
Yes. Yes.
Yes, it is. Sine theta also increase as theta increase. So that this component is increasing. So the force is dragging it down, increases. But the static friction, which is the maximum amount that it can provide, is mu of static times normal force. Again, normal force balance out the y component of gravity. So that's mg cosine theta. Hopefully this will become very familiar to you. Once you see a ramp on the incline, you know the normal force is going to be mg cosine theta. Okay, as theta increase, cosine theta increase or decrease. So if theta goes from 60 degrees to 90 degrees, is cosine theta increasing or decreasing? I know cosine 90 is 0, so from 60 to 90, it is decreasing, yes. The cosine theta is actually decreasing. You can see the force as with the maximum amount of force you can provide to prevent slipping is decreasing, right? So one is increasing, one is decreasing. The force that's dragging it down increases, the force that prevents slipping decreases. So D is correct, very good. Both of this come together at play is responsible for the box eventually begin to slide down. So it's going to pick up an acceleration in a downward direction. Excellent. Okay, now I remember I said static friction is sort of, there's a trap, people tend to get it wrong. So here I'm just gonna give you another question about the static friction and see if you will get it right. I don't think we need to discuss. I'm gonna go ahead and simply present this to you and let you vote. It's about a mass sitting on the incline. Incline has an angle mu. We know the coefficient between the mass and the surface is mu of s. And what's important, it sits at rest. So what is the static friction? I'm gonna let you vote on this. Okay, 85% of the vote already come in. So the rest of you will continue to collect votes for another maybe 20 seconds. Okay, let's take a look at this together. I'm gonna go ahead and end the poll. And sorry, 1 second. This is our results. You can see we're pretty much split half and half between B and C. Okay, so can anybody share with us, what do they think? What do you think the static friction is right now acting on the box? Anybody would like to share with us? How do we figure out the static friction? I remember we did provide a formula.
The normal force times the coefficient. Yeah.
Yes, I provided this formula. So what does this formula tell us? Is it telling us the static friction at all times?
That's telling the maximum static friction.
The maximum value only, because static friction, as we said, really varies you can decide to pull on the object a very little bit or very hard. In both cases, if it's not moving, then the static friction is simply a canceling out the force you exerted, right? So it cannot really have a fixed formula. The fixed formula is for the maximum amount that it can provide. Once you exert a force that exceeds this maximum amount, you're going to start moving the table or the object. So that's the maximum amount, which will be mu s mg of cosine theta, because normal force is mg cosine theta, right? Now, E is this number. Now, do we know for sure that right now the static friction is at its maximum value? It doesn't really tell us. We don't know, right? All we know is the MS is at rest, which means whatever the static friction is, it is going to counterbalance the component of gravity that's pulling it down. Again, this is Fg. The component of that along the x direction is this Fgx, which is mg sine theta. So if it is not moving, there's got to be a friction to balance that. So C is the correct answer. You can see that there's a trap for static friction, right? You might be be tempted to use this formula, but remember that formula is only for a maximum value. Kinetic friction, however, is always use of K times normal force. So that is a fixed value. Now let's talk a little bit about springs. The reason we go through these formulas is because when we do problems, sometimes they have friction, sometimes they have spring. We need to know what these values, how to calculate the forces. So again, for springs, all we talked about in the beginning, when I talk about different forces is, I said, the more you stretch the spring, the bigger the spring force is going to be, right? But exactly what does the formula looks like? It's I mentioned this briefly, but today let's look at this in more detail. The force provided by the spring is proportional to how much you stretch it, how much you compress the spring or stretch the spring. That's delta x. This is Hooke's law. And there is a K here. It's a spring constant. It describes, you imagine you have a spring that's really loose, right? When you drag it, it's going to stretch a lot. There's some spring that's really tough, right? It's wired really closely together and it's really hard to pull. And that's reflected by the spring constant. The spring that's really hard to pull have a big spring constant. So this force is proportional to both the spring constant and the stretch, which makes sense, right? And it's also, there's a negative sign. The negative sign represents the direction of the force because it's always resisting that the pull. Because if you stretch the spring to the right, if you stretch it to the right, then the spring will try to pull you back. The spring force will be pushing to the left. So the force is to the left and the stretch is to the right. They are at the opposite different directions, right? So that's why we put a negative sign here. Likewise, you can compress the spring. If you compress the spring, then to the left, you can push it to the left. Then the force will be pushing you out, right? The force is to the right, always in the opposite direction. That's why we put a negative sign here to describe those relationships. So force is negative K delta X. We call it displacement. Now you can think of this because the displacement will be a vector. So implicitly that will tell you in what direction you're pushing it or pulling it. But you can try to understand what this represents is how much you have stretched or compressed your spring. So let's practice the idea of Hooke's law by looking at this particular question. First of all, you have a spring, and when you put a load of 2 pounds on the spring, it stretches 1 inch. Now you added another 5 pounds. How much will the spring stretch? Not how much more will it stretch, is how much will it stretch overall, as opposed to when it's not stretched at all, okay? Again, this one, I will let you discuss it in groups. for about a couple minutes.
Professor, we can't hear you.
Oh, I wasn't talking. I'm still waiting for the poll.
Oh, okay.
So please, yes, another 20 seconds. So if you haven't voted already, please put in your vote. Another 20 seconds, okay? Okay, any last minute vote before I close the poll? Okay, let's take a look at this together. This is our results, quite evenly split between B and D. I believe that you at least agreed on something because B and D, they're only off by 1 inch. So I think we at least calculated some quantity correct. All right. So I drew this little diagram here to show what's going on. First, you have a string that's not stretched here. Then you put a load on it, 2 pounds, and it is stretched by 1 inch. So implicitly that had told us the spring force that's acting on the block is going to be how many pounds? So that's the force that's provided by the spring on the block. It's going to be how many pounds? It's going to cancel your weight, right? Balance out the weight. And the weight is 2 pounds. So the spring force is going to be 2 pounds. Okay. And now you're putting a bigger weight. So it's going to be 7 pounds. And how much does it stretch? Okay, so if I apply Hooke's law, it's 2 pounds of the spring force. And it's stretched by 1 inch, which means the spring constant. And I take it, if I simply take the absolute value of everything, because I already know the direction is upward, then I can calculate my spring constant, which is 2 pounds over an inch. You can see I can simply keep it as a unit it is. And then I'm going to use this information to calculate what happens when my spring force is now 2 plus 5, 7 pounds, right? Okay, so if your spring force is 7 pounds, how much does it stretch now? So this has to be 7 pounds, right? And I can plug in my K from the previous question because you're still dealing with the same kind of spring. So it's 2 pounds over an inch times delta X prime is 7 pounds. You see your pounds cancel. Your delta X prime is 7 over 2, which is 3.5 inches. 3.5 inches, which is D, is the correct answer. Okay. I think if you said 2.5, you are calculating how much more did it stretch compared with this situation. If you add more weight, it's going to stretch even more. That's 2.5, but it's asking how much will it stretch overall. That is 2.5 and the one that is already stretched. So it's 3.5, okay? D is the correct answer. All right. Before I go on to solve a more complicated problem, I want to ask, are there any questions in terms of how to calculate normal force on the ramp, how to do static and kinetic friction on the ramp, and how to do a spring force? Are there any questions before I move on? You know, when you are muted, you can hit your space bar and hold it and talk, And then when you're done talking, you can release it. So that might be easier than to mute and unmute yourself. So I hope that you would feel free to voice whatever question that you have. Oops, sorry, remove my screen then again. Thank you for Clement's comment. The Alt key plus A, you can also to mute and unmute yourself. Have to be full screen in order to use the space bar. Okay, all right, thank you guys. Thank you for all these suggestions. Any questions? If you don't have any more questions, and we can move on to do a problem together, okay? So now let's apply Newton's second law and do more questions, because now we know how to calculate these forces, various spring force and kinetic friction or static friction. So you'll see, you know, the type of problems, and I kind of break it down, say an incline problem, but it's really just the physics behind it. It's all, they're all connected, right? So an incline problem is not all that different from a spring problem, even though on the surface they may look different. But just for the sake of getting you familiar with the context of a problem, I say, okay, sometimes you see incline, sometimes you see a spring, sometimes you can see a pulley, and sometimes you see, you know, there are multiple objects, not just one object. You have to do free body diagram on 1, 2, or even 3 objects. Right? Sometimes you see problems that use both dynamics and kinematics. So I want to be able to show you all the variety of problems you will see. We'll start with the incline and the spring problem. This problem is great because it is on a ramp. That's a context you'll see a lot, and it also involves using that spring. So we're going to try to do this one together. Here's the example problem. So I'm going to simply read it out. Of course, you can just read it on your own. You have a block, and it's right here sitting on the ramp. It gives us the massive block, the angle of the ramp. It gives us the kinetic coefficient of friction between the block and the ramp, so kind of tell us the information about the surface. Also, the static coefficient is another coefficient. And you have a spring sort of keeping the block from going down. Now the question is very interesting. The question is asking, what is the minimum spring constant of the spring you need in order to keep the block from sliding down if it extends 0.12 meters from its own stretch length? Okay, so it's a quite complicated sentence. There's a lot of information in this question. So first of all, it's telling you at this moment, the spring is stretched. Okay, yes, it's stretched this much. So which means the spring must have provided a force to keep it from sliding, right? Okay. But it's asking what is the minimum spring constant. So you don't want to provide more force than you need to. You just want to say, I'm just going to provide the bare minimum of what is needed in order to keep the block from going down. So can anybody tell us, what do you think the minimum implies? What do you think? How do we calculate this minimum spring constant? Because if you think about all the factors that's making the block slide down or preventing the block from sliding down, right? Various factors at play. So the force that's responsible for the block to go down, that's the component of gravity, right? The X component of the weight. We know that. So other than the spring is trying to pull the block up, there are any other forces that is helping out the spring to keep the block from sliding? What What is that force?
Static friction.
Friction, yes, very good. I didn't quite hear, did you say static friction?
Yeah, to keep it in place.
Thank you, Bridget. It is static friction to keep it in place. Very good. So we now have static friction as well as my spring force to keep it from sliding. And I have the component of gravity to make it go down. So you might imagine gravity got to be a little bit bigger than either one of them because the two of them together prevent the slipping. Okay, so if the spring constant is a minimum, suggesting some other force has to be maximum. Which force is it? Let's say these two guys is like you and your friend pulling your weight together. If you only, you two together have to provide 100 newtons of force. Let's say your friend only provide a bare minimum of 10 newtons, which means you have to provide how many newtons? 90, right? So if the spring is providing a bare minimum of the force, which means the static friction has to be at its maximum, right? So it's like spring talks the static friction. It's like, hey, what is the maximum amount of force you can pull? And the static friction says, I can put in 90 newtons. And the friction, great. And I'm gonna need to provide 10 newtons. That's the minimum I'm going to provide. So that is included in, implies in the question, your static friction now is at its maximum, okay? All right, so knowing that, we can solve the problem. So now I'm gonna go ahead and we're gonna do this together, okay? All right. So the first step in solving these problems, I hope you still are remembering it. The first is draw a picture. Picture is already given, which means I want to label the quantities, label the forces. So draw the free body diagram, okay, and add in the coordinates. So all of that. So now let's do this together. So I'm gonna label the forces. One is Fg is M1G, normal force. Spring force, I don't know, I wanna calculate. Static friction, F of X is at a maximum value. And the weight, the component of gravity that is in the X direction. So I'm gonna say X and Y directions, okay? X is pointing along the ramp, Y is pointing perpendicular to the ramp. So the component of gravity is Fg in the X direction, and you have F of G in the Y direction. This is theta, okay? So I have all these forces. Now, the third part is think about what physics I'm going to use to solve for the question. The physics is Newton's second law. Okay. And the question I'm trying to solve is what is the minimum spring constant so that the block is at rest, okay? Which implies static friction is now at the maximum, which is mu sub x times normal force. So these are implied. Okay, now we're ready. We're ready to solve it together. Okay, now let's apply F net equals ma to the block in both x and y directions. So let's apply it, first of all, in the y direction. F net in the y direction equals ma in the y direction. Okay, hopefully at this stage, you're very familiar with our process. There are two forces in the Y. One is the normal force, one is the component of gravity that's in the opposite direction. So that's why you have a negative sign, equals m times 0, 0 acceleration in the Y equals 0. So this tells me the normal force is equal to FGY, just mg cosine theta. Don't plug in numbers yet. We'll do the number plugging at the end. So here I'm going to express my results using the quantities variables that is given. So m is given. We know the mass, right? We know the theta. So I'm going to keep it as mg cosine theta. Now let's apply in the x direction. F net of x equals max. Okay, so how do I represent all the forces in the x direction? How do I expand this? Anybody would like to help us to write the left-hand side of this equation? How do I write the left-hand side of the equation? You just simply add up all the forces in the x direction. If it's in the positive direction, you say positive. If it's negative, you add a negative sign. Anybody? Okay, Gabriel, thank you for typing this in the chat. F of g's of x, yes, you have the s of g of x in the negative direction. Because I have decided the positive to be upward. You can totally decide the downward to be positive. That's up to you. Very good. So that's going to be negative s of g in the x direction. That's one of the forces. I still got two more, right? So one of them is F of s that you said. What is the other one? Spring force, thank you, Haider. It's spring force, and that's positive as well. And they equal to 0 because the block is not moving down, right? Okay, now let me further expand some of these quantities. I know x component of gravity is mg sine theta. This should come very quickly to you. Okay, the x component of gravity is on the ramp is always mg sine theta. The maximum value for static friction, because we now know it's at the maximum value, is mu of x, mu of s times normal force plus the force of the spring, okay? We know normal force, so let's plug in normal force. So force of the spring is mg sine theta minus mu times normal force mg of cosine theta. I have calculated what my spring force is. Okay, and is that what we're trying to solve? We're trying to solve spring constant. So I need the K. Okay, that's not too bad, too hard. I can plug in K, delta X. Because I'm dealing with simply the magnitude here, I just need the absolute value. So K times delta X is mg sine theta minus mu of S mg cosine theta. And the rest is simply plugging numbers, right? You want to know what K is mg sine theta minus mu cosine theta over delta X. Okay, at this stage, I'm done. Only at this stage, I'm start plugging numbers. I first take a look at my expression. I see, okay, has a unit of this Newton, which is Newton. Sine theta doesn't have any units over length quantity. So that is the correct dimension. So I'm gonna plug in numbers. M is, what is M? 8.7 kilograms. G is 9.8 meters per second squared. Sine of 38 degrees minus, okay, I don't have enough space, so Mu is 0.45 times cosine of 38 degrees on the top. Delta X is 0.12 meters. Putting everything together, you get K is 230, roughly 230 newtons per meter. So that's the spring constant you need, right? Which means that tells you how strong of a spring you need in order to prevent the block from sliding. And it's only gonna be stretched by 12 centimeters. Of course, you can stretch more, but we're looking for, at this amount of stretching, what is the minimum spring force you can get away without the block sliding down. So that's how we did the problem. Okay, so it looks complicated, but you can see once we break it down into X and Y very carefully, hopefully that is not, is straightforward, it's not too complicated, okay? All right, but that's actually all for today. Next week, I believe we have 2 more discussions on Newton's laws. We're gonna do problems again on Newton's second law, and then we are going to do Newton's third law, and then we'll be done. Okay, so go back to the question. It's right here. Okay, so that's all for today. If you have any questions, feel free to ask. We still got a couple minutes left. If not, I'll see you guys on Thursday. And don't forget that our office hours are the Wednesdays and Thursdays, okay?
Have a nice day, Professor.
Have a good one, Professor.
Thank you, Professor. Have a good day.
Hey.
Thank you.
Thank you. Is this the slide you're looking for?
Professor.
Yes.
I have a question. Mostly about one of the homework questions.
Yeah, sure.
So one of them is asking, it's for this week's homework, it's asking what the net force that box B exerts on box A. I've been trying to remember how to find that, but I just can't.
Oh, you're asking on flipped physics, right?
Yeah.
Okay, let me, give me 1 second, let me bring it up. But can we, actually, can you go to, why don't you go to my office hour link, because this will be a video and it's recorded for class. Can we meet at the office hour link real quick?
Yeah.
Okay,
sure.
I'm gonna exit from here and I'll meet you there, okay?
Okay. I have a question as well. Do I go there as well, Professor?
Yeah, go ahead. We all go there.